Cool. Good afternoon, everyone. I can't see you currently, so I imagine people are still joining, but I guess we'll make a start either way. So I'm Ben. I'm the RMET's Science Engagement Fellow for Energy. And this afternoon, we've got the seasonal forecast outlook for the energy sector for the upcoming winter. And just to let you know that this event is being recorded. So we'll get straight into it. So first of all, some top tips on Zoom. I know at Reading we use Teams, so many of you might not be familiar with Zoom. So we're going to collate questions for speakers in the Q&A box, which you should just be able to see at the bottom there. You can also upvote these questions, and I will be asking these questions during the Q&A session just after 3. And yeah, they'll just be sorted by the number of upvotes received. So if you do have any questions, please put those in the Q&A box and we'll get around to them at the end. So I guess just more Zoom stuff as well. If you want to make the PowerPoint slide bigger, you can close the chat and enlarge the screen. And if you're having any technical issues, I guess try turning it off and on again or leaving the meeting and rejoining. I find Chrome works quite well for me. So first, just an introduction to RMET and the energy sector. So I'm, as I previously mentioned, the Science Engagement Fellow for Energy. And RMET sort of acts as a bridge between weather and climate scientists and the energy sector. So by providing networking opportunities, various training opportunities and events like these, but also through RMET's publishing activities as well. So we have the special interest group, which meets around 3 times a year to discuss how RMET can support the energy sector through these activities, which is chaired by David Brayshaw at the University of Reading and Daphne Sivaniotti at EDF. And facilitated by myself, Hannah Mallinson, and Beth Woodhams at RMET. So if you'd like to be involved in the special interest group, or if you would like to enroll in our email newsletter, you can just follow this link here. And also, if you have any questions, you can contact myself or Hannah at the energy@rmet email in the bottom there. Yeah, on there. So to outline the programme for this afternoon, so first we have the seasonal forecast outlook for the winter being presented by Hazel Thornton from the UK Met Office. Hazel will also be providing an introduction to seasonal forecasts for any of those unfamiliar or who maybe just need a reminder. Following that, we have Antje Weisheimer from Oxford and ECMWF, who will be essentially reflecting on the seasonal forecast outlook and providing perspective from the European Centre. And then we'll move on to our talks from those within the sector. So Lucy Field from EFRI talking about gas markets and how this forecast might influence them. And then Isla Finney from Lake Street Consulting, talking more broadly about how they do work with stakeholders to use these forecasts. Like I previously mentioned, we'll have the panel discussion following that just at 3:05. And so we've got about 20-25 minutes for questions, and then we'll close at 3:30. So finally, just a reminder that if you're not an RMET member, then there's many benefits to becoming one. So you can get a print or online copy of the monthly journal Weather. You can get free online access to many of the journals, so QJ, iJOC, and Wire's Climate Change, probably Met Apps as well. You can receive a monthly email newsletter. For me as a PhD student, discounts at conferences and access to support grants is very useful. So definitely if you're a PhD or early careers researcher, it's worth becoming a member. So that's it from me for now. So I'm going to shortly pass over to Hazel Thornton, who is the manager of the monthly to decadal prediction and impacts team at the Met Office Hadley Centre and has long experience in applying climate science to support stakeholders in government and the private sector. Hazel's own research focuses on North Atlantic and European climate variability and predictability, exploring their effect on renewable energy balancing. She has a range of publications covering climate variability, climate predictability, climate adaptation, and data assimilation. Hazel's team is currently researching the seasonal and decadal predictability of a variety of climate extremes, including windstorms and droughts, and their associated impact on different sectors, including energy, water, and infrastructure. So I'll just stop sharing my screen, and Hazel will share her screen just now.
Good afternoon, everyone. Thank you very much, Ben, for the introduction. As Ben said, I sit within the monthly decadal prediction area of the Met Office, and it's thanks to the wider seasonal forecasting team for the forecast that I'm going to be presenting today. As Ben said, I'll give a quick introduction to seasonal forecasting, particularly what's relevant for our area, focusing on climate drivers that can affect the UK winter climate. And then I'll give the Met Office's December average forecast and the December, January, February average forecast. So just to cast our minds back, obviously the UK has a very variable climate, as we know, and this just shows two media pictures from December 2010 and December 2015, when we had very different December weathers. So we remember December 2010 was during a negative NAO pattern where we had lots of cold, snowy conditions, calm conditions, whilst December 2015 had many storms and obviously flooding. So the big question is, what will the winter of 2024 and 25 look like? And this is all about seasonal forecasting. So what do we need to be able to model to accurately forecast the winter weather? So there's something called the North Atlantic Oscillation. So for those that aren't familiar, a quick recap. So if we focus on the picture here on the left, basically the North Atlantic Oscillation is a pressure gradient between Iceland, where we typically have a lower pressure, and the Azores, where we have higher pressure. And the strength of the gradient between the two determines the strength of the storm track and the types of weather that we get in winter. So a positive phase of the NAO is when this low pressure is low and this high pressure is high. So this gradient is strong with an active storm track, and this often leads to a mild, wet and windy winter with lots of storms. Conversely, when we have a negative phase, the low pressure over Iceland is not as strong as normal, and the high pressure over the Azores is not as strong either. And then we have a weaker storm track, and often a greater chance of having high pressure and blocking patterns, giving colder, calmer and drier conditions. So this is the time series of the NAO over the last 20 years or so in black. And so we have above zero being your positive phase and below zero your negative phase. So this is the variability we see. And for example, that 2015, the flooding winter is here. You can see the highest in this record. And the 2010, I think it was this one, but you can see here's a couple of years when we had very negative NAO winters with cold and calm. And so what I'm actually showing here in the colours is the forecast. So we give a seasonal forecast of the North Atlantic Oscillation and the weather over the UK using a fully coupled ocean atmosphere model. And the individual ensemble members, so different runs of the model, are shown in the orange dots. And the ensemble mean is given by the orange line. And this is basically what we use as a forecast, because we only have forecast with that ensemble mean, forecast skill with the ensemble mean. And basically, Adam showed that back in 2014, so about 10 years ago, that with the system that we had then, we had statistically significant skill in forecasting the winter NAO. Not always correct. There are bust years when, for example, in 2005, where the model was going for a negative NAO, but it was actually a positive NAO pattern. But other years where, as you can see, these negative NAO years we successfully forecast. In blue, this was in hindcast mode when we look back retrospectively. In blue is the actual real-time forecasts. So this is what's happened since using that system. And basically, for both the last 10 years, but also the hindcast as well, both have a correlation of a Pearson correlation of about 0.5, 0.6 between the observations and the forecasts. So we do have skill on average. That doesn't mean for a particular winter that it's going to be correct. And this is also now the case for a number of seasonal prediction systems. And one of the key parts we'll be showing is when we give a forecast, we don't just use the Met Office forecast results. We also look at other modelling centres results and use those when we're interpreting the forecast. Okay, so why is the NAO important for UK energy security. So I've actually done some work on this myself. And as I just highlighted, when we have a positive NEO, that's when we have a strong storm track and more storms, windier winds from the west. Obviously, we're going to get more wind power on average during the winter. And that typically gives milder temperatures and reduced demand. So this is, here we have a graph where we're showing the percentiles of electricity demand. So this is low demand, and this is high demand days, so over the winter. And this is the average pressure pattern during those low demand days. So we can see that, as described, we have the situation where when we have an NAO positive pattern, we have low demand, but good high wind power, which is on this y-axis. However, unfortunately, as we move through higher demand, so as the temperatures basically get colder, our wind power reduces. And this is because of having typically a negative NAO pattern where we have easterly winds, so cold winds, a calm associated with a high pressure, cold and calm. So unfortunately, we have this sort of the relationship we wouldn't necessarily choose. Obviously, with higher demand, you'd prefer to have higher wind power availability. Unfortunately, in the UK, that isn't typically the case. You do occasionally have cases, for example, the beast from the east, where you would have a strong easterly winds, but typically it's the case that when you have higher demand, you have lower wind power. So this is why understanding atmospheric circulation matters for energy security. And when we're forecasting the winter, obviously you can run your model and get an output, but you really want to understand whether the model reproduces the key features of the climate system that affect the NAO. And this just shows some of the drivers that can affect the NAO. So, for example, I'm sure you're familiar, this is a picture of sea surface temperatures across the globe, and this is the East Pacific, where the El Nino Southern Oscillation plays an important role in global climate and for us in winter over the North Atlantic. Other internal variability includes the stratosphere, what's going on in the stratosphere, both in the tropics and also at the polar regions. That can affect what the winters could look like. And then you have external factors such as volcanic eruptions or solar radiation maximums. Okay, so my plan is to give you a forecast describe what's the current state of the climate system and our forecast of the climate system, and then give you a specific forecast for the UK. So the biggest driver of global climate variability at the interannual timescale is the El Nino Southern Oscillation. And as I just said, this is a picture of sea surface temperatures from, this is from the 10th of November to the 16th of November, so a recent snapshot of global ocean temperatures. And what you can see when we're focusing on what's happening in the Pacific near the equator, we can see we have slightly lower temperatures in the East Pacific and slightly warmer temperatures in the West Pacific. And this is a signature of a very weak La Nina. And so the current status, there are various different measures for categorizing a La Nina or an El Nino. And the current status is we're neutral and just on the border of a weak La Nina. And then here we have forecasts, both from the Met Office system and then the multi-model C3S system. And basically, this is the surface temperature of what's called the Nino 3.4, which is basically a region in the Central Pacific. And a La Nina is categorized if you go somewhere below 0.5 to 0.8 degrees Kelvin for a sustained period of time. So basically our forecast is a slight increase in the negative temperature anomaly, but not much change really from the current situation. And this is pretty similar in the C3S model. So individual models, some of them are going for a weak La Nina, some of them are going for neutral, but it's basically not a particularly strong driver this winter. But if there is a push, it's for the La Nina direction. So what does La Nina mean for our UK climate? So this shows the mean sea level pressure anomaly that you get when you have a La Nina historically in observations. So just to orientate yourselves, the UK is here and this is Greenland, so this is the North Atlantic. And when you have a La Nina in early winter, so November and December, you will typically have a high pressure anomaly to the west of the UK. So you're going to have sort of northwesterly winds in that sort of early November, December period, and more of a block to the storms coming from the west. Whilst in late winter, it's a different signal. So in January, February, it's a signature where you have lower than average pressure over the polar cap, and then higher than average pressure to the south of the North Atlantic. And this leads to westerly winds and more zonal winds, so more winds tracking a latitude band. So this is typically a wet, windy, warm winter. So this is the standard La Nina teleconnection. It can be overridden by other things if it's not strong, but this is on average what happens when you have a La Nina. A second drive is something called the quasi-biennial oscillation, or the QBO for short. And this is looking at winds in the tropical region of the stratosphere. So above the troposphere into the stratosphere. So we're looking at pressure heights of about 20 to 50 hectopascals. And basically what happens is the winds move from going from westerly to easterly, then from easterly to westerly. So every couple of years, approximately, they swap directions. So this is going through time, for example, from 1980 through to 1990, all the way through to 2023. And you can see that we oscillate between a westerly wind direction and then easterly, then a westerly, then an easterly. So those winds are changing every couple of years. And this has been shown to have an impact on the surface. So this is a paper, an old paper, but it shows that when you have a QBO easterly minus westerly, that you have typically over our region of the world colder temperatures. So these are temperature anomalies. So with an easterly QBO, you have an increased chance of cold, dry, and calm winter, and the opposite when you have a westerly QBO. So what do we have at the moment? This is through time along the bottom, and then this is with height, and this shows that this is the zonal mean zonal wind at the equator, and reds mean it's westerly, so going from west to east, the wind direction. So this is basically what we're terming as a westerly QBO, with the wind slowly descending through time, and this is where we are today, and this is a forecast. From this side is a forecast, these are the obs, and so we're in a westerly QBO phase. So that means that we have an increased chance of a strong stratospheric polar vortex. So these are the winds around the polar vortex. I'll talk about that in a minute, particularly in December and January. And that leads to an increased chance of westerly winds over Northwest Europe. So sort of warm, wet, windy, late midwinter. Another driver that's very important for our winter weather is something called the sun stratospheric warming, and this is looking at the circulation in the stratosphere, so the higher above the troposphere, over the North Pole. So here's the UK, here's Greenland, here's our North Pole, and this shows basically the arrows are quite faint, but hopefully you can see that in a typically over winter we have westerly winds rotating around the pole. However, when we have a sun stratospheric warming, that circulation is completely broken up, and it can the polar vortex can either break into two, as shown here. So you have two separate ones, or the vortex doesn't break up, but it moves off, shifts off to the side. And again, this has been studied at length, but it's been shown that that can influence the surface at the surface over the coming 2-month period after a stratospheric warming event. So this just shows that when you have a breakup of the vortex, you typically have cold temperature over much of the Northern Hemisphere, including the UK. So this is an important event. You expect to have one every couple of years, and not every time you have an event does it lead to cold temperatures, but in about 60% of cases, when you have a stratospheric warming, it leads to cold European temperatures. So keeping an eye on whether we're going to have a sun stratospheric warming is a good useful predictor of European temperatures. So what's our forecast for whether we're going to have a stratospheric warming or not? So currently, this is the strength of, so this is through time, This is over the winter period. This is the strength of the zonal mean zonal winds. So that's the strength of that vortex, the winds around the pole, the North Pole in the stratosphere. Dark blue is the average over climatology, so over all many different winters, and the range you can get. And then the forecast is shown in red. So you can see at the moment, we have a strong polar vortex, so the winds are really strong around the North Pole, and it's predicted to remain so for much of the winter period. So that is our forecast at the moment. However, we don't have deterministic skill in predicting the start of stratospheric warming beyond about 2 weeks. And so it really is something to keep an eye on, because these things can evolve rapidly. And if we do get a stratospheric warming happening, then it can shift completely the forecast for the next month or so. Okay, and the final climate driver I want to talk about is the response of our region to a solar maximum. So this is the activity of the sun, and this is the sunspot number, and it shows through time again that there's this 11-year cycle, and we're actually at a solar maximum at the moment. And others have, this is Leslie Gray and others have done studies to try and identify what's the impact of a solar maximum on European climate, especially winter European climate, and it is complicated for sure. But one of the signals that has come out is that the impact varies over the winter period, and that actually involving the strength of the polar vortex again, and it can lead to basically lower pressure. This is a pressure pattern field, but basically it can lead to more NAO positive like conditions in late winter. So sort of more wet, windy UK weather in late winter, whilst it's reverse in early winter. But this is more related, not so much to do with the polar vortex, but lags of sea surface temperature. Anyway, so that's an additional driver for us to consider at this point, given we're at the solar maximum. So that's all the different drivers. I'm now going to talk about the forecast for both 1 month mean for December and then the December, January, February. And it's just worth saying that, as I said before, it's not just using the Met Office modelling results, but we incorporate results from other modelling centres and use knowledge on observations and expert judgment to make the final forecast. So this shows the forecast for December mean sea level pressure anomalies, where red is a positive pressure anomaly and blue is a negative pressure anomaly, from the Met Office, from the European Centre, from the Korean Met Agency, and from Météo France. And as you can see, they're quite consistent in their forecast this is the UK here, of high pressure to the west of the UK, with these northwesterly winds affecting the UK in nearly all the systems. So that high pressure has the result of reducing the likelihood of storms coming across to the UK and more northerly and northwesterly winds. So what does that mean for our forecast? I'll just take a second to explain these if you haven't seen them before, but this is UK mean temperature forecast here. This next plot is precipitation accumulation, so rainfall and snowfall. And then we have an average wind speed forecast. And in the dashed line is the climatology. So this is from 1990 to 2020. This is the distribution of UK mean temperatures over that period. And then the forecast is shown in grey. So with the climatology, so if you just focus on this dashed line, we categorise into 3 categories of near average temperatures, which is the central 60%, and then a cold category, which is 20%, and a mild category, which is 20%. So we have a near average and then a cold and a mild, and the same then for dry, wet, calm, and windy. And then we look at the shift when we give the forecast using the seasonal forecasting system. We look at the shift in the likelihood of these different categories. So what we can see here for the UK temperature is that it's a small shift of mild UK winter temperatures, moving from 20 to 25%, so an increase of 1.3 times the risk of a mild winter. Cold is the same as normal at 20%. and then it's just the near average that is slightly reduced. So it's a small increase in the chance of a mild month. Now, given we've just shown that it's a northwesterly flow, you might have expected a slightly cooler temperature, but obviously we're considering a period from 1991 to 2020, and actually having a risk of 20% of a cold category is actually higher than it has been of late, because we can see this is the categories, this is what actually happened for the last 10 years. You can see we've had lots of milds, and that's because of the general global warming and moving towards a warmer climate. So the fact that the cold likelihood is 20% is rare in the last few years. For precipitation, we're having a slight shift towards drier conditions, but again, you can still see the likelihood, the most likely is going to be a near average with 6% chance, but there's a 25% chance of dry and a 15% chance of wet. And for winds, there's a slight increase in the chance of calmer conditions. But again, the most likely is still near average, but that likelihood of calm is increased, and that's because of that blocking high pressure, which reduces the likelihood of storms coming through. Okay, so just in words, the chance of a cold month is close to normal. Nevertheless, this level of likelihood is greater than typically seen in recent years. There's a slight increase in the chance of dry month compared to normal, and there's a slight increased chance of calm December compared to normal. Okay, so now looking at the 3-month average, where we're not trying to forecast at any given day, but the average conditions over that 3-month period. Here we have the mean sea level pressure anomaly forecasts from the different centres again. And again, the picture is actually of a NAO positive winter, where we have lower pressure to the north and higher pressure to the south. And from the Met Office system, it's nearly zonal. So the winds that would give you strong westerly winds, so a relatively strong pressure gradient, a positive NAO with westerly winds, wet, stormy, warm, windy winter. It's quite similar for ECMWF forecast. If we look at, for example, Météo France, the high pressure is slightly further north, so the UK actually sits under the high pressure. And obviously, if that's the case, then it's more similar to what we're having in December average, where the UK is sort of blocked slightly by this high pressure. So, you know, the devil is in the detail. Most of the systems are going for a zonal flow, which you will see reflected in these forecasts, Met Office forecasts. So again, this is the same plots, but for the December, January, February mean. And here we can see a clear shift in the forecast to mild conditions and away from cold. So the likelihood of a cold winter is only 0.3 times the normal risk, whilst the likelihood of a mild winter is over 2 times what it would normally be. We're forecasting a wet winter. Well, there's a 30% increased risk of a wet winter, so that's 1.5 times the normal risk. There is still a 5% risk of a dry winter, so it's not that it's not there, it's just it's much lower. Still, the near average is the most likely. And then for also a windy winter, so there's an increased risk, a near doubling of the risk of a windy winter, and a small risk of a calm winter. Okay, so just in words, overall, the chance of a winter being cold is lower than normal. However, this doesn't preclude some cold spells and related impacts. So you can still get blocking high pressures, which will give you those colder spells. There's an increased chance of winter overall being wetter and windier than normal, and stormy conditions and impacts from high winds are more likely than for a normal winter. Okay, thank you. That's all I have. Oh, one last thing. So the Met Office gives monthly briefings to the energy sector. It's open to everyone. Every month we've had a couple, and we've got 2 more, one in late December for January, February, March, and one at the end of January for February, March, April. And so these are, you know, we're running the model every day, so we're always having an updated forecast, and we communicate this once a month. So it's really important that if, for example, you have a stratospheric warming, that you log in to see what, if you're keen to understand what it means for you, that you keep updated. So just a reminder of that. Thanks very much.
Perfect. Thank you, Hazel. And thanks for sharing that about the energy sector briefings at the end. We'll now move on to Antje Weisheimer from ECMWF. So Antje is a senior scientist in the Earth System Predictability Group at the European Centre for Medium Range Weather Forecast, where she mainly works on seasonal forecasting. She also holds a joint research position at the Physics Department at the University of Oxford, leading the Predictability of Weather and Climate Group. Thank you, Antje.
Thank you very much, Ben, and good afternoon, everyone. So as Ben mentioned, I come from ECMWF, also work at Oxford, but today I present here the results from the ECMWF seasonal forecasting system that we run operationally. So our forecasting system is called CEAS5, it's the 5th generation of our seasonal forecasting system, and this comes with thanks to my colleagues here in the seasonal forecasting team at ECMWF and colleagues also from the Copernicus C3S climate change service. There will be some overlap with Hazel's presentation because the forecasts are to some extent quite similar, gives us some confidence, I hope. But let me start with the factor that provides the largest individual source of predictability on seasonal timescale, which is the variation of the surface temperatures of the Pacific Ocean in the equatorial region, the ENSO phenomena. It's important to look at this to see whether we get any driving signal from the tropics that might influence the weather or the climate in other parts of the world. So here we see the Niño 4.3 SST forecast plumes from our system, and the little map at the top right shows you the Niño 3.4 region is in the center of the Pacific, of the tropical Pacific, ±5 degrees around the equator, and it's a good indicator of the status of El Niño. And we start off at the beginning of November here in these forecasts with roughly 0.5 degree colder than normal SSTs in that region. And the predictions in red, as you see here, the individual ensemble members, it's 51 members, all indicate slightly cold anomalies, colder conditions throughout the coming winter across this region, and it's also the same for other parts of the tropical equatorial Pacific here. So it's a weak La Nina condition. I think Hazel mentioned that as well. It's not considered a very strong La Nina, but it's colder than normal conditions. If we now look at the forecast, and we see here global maps for the 2-meter temperature forecast from our system for the DJF season, I should first say the forecast start dates of these predictions is always in the 1st of November. So we look at the DJF season from these predictions here. We consider 51 ensemble members, and we compute the anomalies with respect to a climate reference period from 1993 to 2016. On the left-hand plot, of the left-hand side, the plot shows you the ensemble mean anomalies, where the reddish colors give you warm anomalies. Everything around white has no signal. The little green lines is indications of significance, statistical significance, and then the bluish colors give you cold temperatures. And you see the weak La Nina conditions here as well, stretching across the equatorial Pacific. You see mostly red colors in the northern hemisphere, especially over the continents, over the North American part, and over Eurasia, going into more the eastern parts, northern parts of Europe here. I saw there was a question about the climate change signals in the trend, and yes, undoubtedly this will be reflected in some of these forecasts here. It's more an attribution question, but it's clearly a factor that's coming into play here. On the right-hand side is also the forecast for the 2-meter temperature, but it's now looked at it from the probabilistic point of view. We have an ensemble and we produce probabilistic forecasts. The way we present it here in one plot is a summary of several aspects. So we first look at 3 categories, a little bit similar to Hazel's, but we're looking at equally likely categories, tercile categories, lower terciles, middle tercile, and upper terciles, the warm events. And then we, for each grid point, we color here the probability of the most likely category for each of these grid points. So all the reddish colors indicate those grid points where the most likely category is on the upper tercile, in the warm category. And then the shades of the yellow and orange give you the probability ranges there. And then the white areas are those with sort of the neutral tercile categories, and the blue areas give you the probabilities for colder events there. And these maps are consistent in indicating large areas of the world are predicted to be warmer than in the climatological part of in our climatology from the model. And we see the colder parts in the tropical Pacific related to the expected weak La Nina conditions there. If we look at precipitation, we see here a map, again, displayed as the probability of the most likely category, like I explained for the temperature in the previous plot. So the brownish colors indicate areas where the forecast goes for most likely drier condition than normal, and the green shades, the probabilities of being in the most likely wetter category. And if we look at our part of the world, Europe, the UK, we see that there's quite a band of green, light green colors in that part of over the Atlantic there into the northern parts of the UK and Scandinavia, North Sea, with increased probabilities for wetter conditions. And then we see in the south of Europe, you see the Iberian Peninsula especially, and the subtropical parts of the Atlantic, we have higher increased probabilities for dry conditions. So if you look at Northern Europe, it's most likely wetter conditions, and in Southern Europe, it's the opposite here. So the precipitation and partly the temperature signals are very much influenced by what's going on in the atmosphere in terms of circulation. And here we see a map of the forecast for the ensemble mean sea level pressure anomalies for the DJF season. And that very much reflects what Hazel was talking about in terms of the NAO over the North Atlantic region. We see a clear pattern of a positive NAO anomaly with lower than average pressure in the northern parts, north of Iceland here, and increased subtropical Azores high, which creates a strong pressure gradient, and that of course has implications for the wind and the energy sector. I should say that where exactly this gradient is strongest is difficult to predict. So we, in the seasonal forecasting context, we're mostly looking at the larger scale structures here, and we have certain confidence in the larger scale pattern of the positive NAO, but where exactly the extent of the centers of this oscillation will be located is a matter of uncertainty. And Hazel mentioned that one of the models, for instance, had that positive part of the NAO pattern, this more subtropical one, and further into Europe, which then would give you a different prediction, and if it was slightly shifted southward. This brings me really to the topic of, we see these forecasts, but the question we all probably have in the back of our minds is how much can we trust these forecasts for this winter? And there are three aspects I would like to talk about. One is past forecast skill that we can estimate. Second one is known observed drivers, physical drivers mechanism that can create some confidence in our forecast that we have. And lastly, a comparison with recent similar winters into predictions. Might be interesting to reflect on those. So coming to the first point, the past skill, how good were the forecasts in the past over the context of our hindcast? We're looking here at the hindcast from the reference periods I mentioned before. The measure on the left here that you see for 2 meter temperature is the ROC skill score, which is a measure of probabilistic skill score. And we're looking here specifically at warm events, because most of the time now we get warm events, partly due to the global warming effect. So we're looking at upper tercile events, how well in a probabilistic sense warm events were predicted. And the red colors indicate positive skill. And if you see a little dot in the grid box, that means the skill is even significant. So over the North Atlantic area and parts of the UK, we see significant positive skill for 2 meter temperature. That gives us some confidence. If we then wonder what happens about the circulation that I mentioned before. The NAO, very much an imprint of the atmospheric circulation. We see a map of skill here. This is now not the rock skill score, it's just the ensemble mean correlation with observations. It's another more simpler way of measuring the skill. You'll see the picture looks slightly different for our part of the world. We do see warm colors, which is positive correlations over the northern parts of the North Atlantic and for some of the subtropical, tropical parts. But it's hard to not see the gray lack of skill in the area that is closest to the British Isles here, which means we don't have that much confidence from the atmospheric circulation forecast of the past. So there's some limited skill for the sea level pressure fields. But as I mentioned, the past performance skill is perhaps only one contribution to our overall trust in the forecast. Another one is really the physical drivers, the mechanisms that would create these connections and that give us anomalies in our parts of the world here. And the first one, Hazel mentioned it already, El Nino. What are the connections between past, say, El Nino events, similar El Nino events to what we have this winter, say La Nina conditions, colder conditions in the tropical Pacific, to what we see in Europe and over the North Atlantic. The canonical La Nina teleconnections derive from a long record of observations, really, go such that if we have cooler equatorial Pacific sea surface temperature, these are linked with weaker Aleutian low pressure anomalies, so basically positive anomalies, so weaker Aleutian low in the North Pacific, which then can lead to a reduced wave flux into the stratosphere, which then means there's less perturbation, less disruption to the polar vortex, which implies a stronger, more stable polar vortex, which is then related to a more positive phase of the NAO over the Atlantic. So that's the link here. And we see composite plots here from Chris O'Reilly's very nice blog, where he split it up between early parts of the winter, late parts of the winter. But if you concentrate on the late part of the winter and maybe take a little bit of the December in there to get a picture for the DGF season, you end up with the imprint of a positive NAO from this purely empirical teleconnection from La Nina conditions. So what does that mean for the CEAS5 forecast? If you look at the SST map at the bottom left there, you clearly see the imprint from the weak La Nina conditions that we meant. If you then look at the Aleutian low, we do see a positive anomaly in agreement with the canonical pathway of these La Nina teleconnection. That means a weaker low, so weaker perturbations of the wave propagations into the stratosphere. If you look at the stratosphere, which is a plot at the right here, it shows a forecast for disruption of the stratosphere, stratospheric warmings basically. And in orange, the orange lines is the climatology throughout the winter into the spring season from our forecasting system, and in blue is the forecast for this year. And you see the blue, the forecast for this year hardly ever reaches the climatological probability. So it's quite a strong forecasted stratospheric vortex this winter. And then the forecast of the sea level pressure, we saw that before, reflects this positive NAO. So these forecasts are consistent with what we know from the observed La Nina teleconnections. A second driver is comes from the stratosphere, from the tropical quasi-biennial oscillation. And we are currently in a deep westerly phase. As you see here, these are observations from Singapore, based on constructions of observations from Radisson data from the tropics here. Westerly QBO is related again to an imprint of subjects on a positive NAO. You would expect from purely the QBO relationships a positive NAO. So both the El Nino conditions and the QBO, the stratospheric conditions, point towards a positive NAO, and this is what our model shows. However, we might want to look at some previous cases just as a demonstration what can happen. And the most recent case that I found that looked reasonably similar was the winter of 2020-21. You see on the left-hand side the forecast for the SST, issued from the November forecast. And on the right-hand side, the ones that we're looking at here for this coming winter, they look similar in the sense of that we see colder conditions in the tropical Pacific. The SST, the cold anomalies were stronger in 2020 than this year, but the overall pattern has some similarity. And also the QBO was in a similar phase. We were also in the QBO West in that winter. So similar driver conditions. The verification for the SSTs for that winter 2020-21 turned out to be in quite good agreement overall. I think it was a good forecast of the global SSTs. We see the cold conditions in the tropical Pacific and the extratropical SSTs were also reasonably well predicted. What happened in the atmospheric circulation is a slightly different story. And we see that here in terms of sea level pressure. So similar to this year's winter, the winter forecast for 2021 also showed a positive NAO. For similar reasons, you could say, argue for the drivers, consistent with the canonical observed teleconnections. However, what was then verified, observed in that winter was completely opposite. So the signal that we predicted for good reasons did not materialize in the real world. And we should be aware of that there's lots of unpredictable factors, and Hazel mentioned some of them. The stratospheric warmings are unpredictable on the timescales we are looking at here, subseasonal variability. Similar events in the tropics, like the Madden-Julian oscillations, we can't predict the onset of those, and they can have noticeable impact. So this is like a warning that even though the mean signal is towards positive NAO conditions, the uncertainty is large, and it does by no way mean that this will happen in the real world, as I'm sure you're aware. And with this, I would like to thank you, and I'm happy to answer any questions later in the panel discussion, I think.
Perfect. Thank you, Antje. Really interesting stuff. So we'll now move on to our speakers from industry. So first up, we have Lucy Field from AFRI. So as a nice surprise today, we have Lucy Field and Isla in both the same room. So hopefully that will be helpful for questions later. So Lucy has over 25 years experience in the energy business, most of which has been spent evaluating gas assets, studying security of supply, and projecting energy transition scenarios. So more recently, Lucy's work has been in the development of green gases, so biomethane, hydrogen, syngas. And she also recently completed a project managing the pre-feasibility study for the Nordic-Baltic hydrogen corridor. So I'll hand it over to Lucy.
Hi, everything okay, Ben? Can you see my slides okay?
So I can see your presenter view. I don't know why it's doing that.
Okay, my presenter view.
Maybe try it again.
How is that?
That looks good to me.
Okay, right, well, we'll go with that. Okay, so I'm here to dumb it down a little bit. You'll see what somebody in industry actually understands about weather. So you're going to see some icons of suns, and quite a simple approach. So the gas market, which is my speciality, is affected by weather all over the globe. Gas demand is dominant in the northern hemisphere. So it means that we have colder winters, as in the UK, all over the globe is where the gas demand hits at the same sort of time. But the weather in Brazil can affect the gas prices in the UK. Generally speaking, the closer the weather will have more of an impact on the price. But some markets are huge, like China, and so big weather there can have quite a big impact. I've put together a bit of a story behind some of the changes in gas prices. So if there's no rain in Brazil, then they have limited hydropower, which means they have to have more gas-fired power, which means they import more LNG, which leads to higher global LNG prices, and then higher prices in the UK. But if it's very hot weather in some parts of the US, Japan or China, then there's more air conditioning, which leads to higher electricity demand, more gas-fired power generation, more LNG imports, higher LNG prices, and higher prices in the UK. It's very Cold in China, these are all things that have happened at various times in the last 4 years. They use quite a lot of gas and heating in China. So if it's very cold, then the gas demand does go up and they import more LNG and they have higher LNG prices and prices go up in the UK. If it's nice and windy in Europe, and we've had a few mentions of the amount of wind there's going to be, then there's higher wind power production, which means they need less gas-fired generation, so there are lower prices in the UK. And of course, the opposite is true. If it's not very windy, you can get higher gas prices. And that's, in my opinion, very hard to predict, but everybody here might know, obviously there's been some predictions as to how windy it's going to be. And of course, if there's no sun in the UK, that's just normal. I wrote this yesterday and it was very grey, so that's why that got in there. And that's why there's a nice blue sky on your right. I picked a picture with a bit of blue for us. So cold weather affects gas prices, as I say. We're dominant in the Northern Hemisphere, so it tends to be cold around in January. And the UK prices, or Great Britain, because that's actually the gas market, the NBP and at GB, is higher priced in the winter than in the Netherlands on the continent, because in the continent they have a lot of gas storage, and that just softens the peaks because they can take gas out of storage in the winter, so they don't get quite such high prices. Can't do that so much in GB, so you get higher prices in the winter, and you tend to import gas from the continent from their storage facilities. So we're using the continental storage a bit, and we import gas, but we end up with higher winter prices. And in the summer, we have slightly lower prices because we're not putting gas into storage, so the demand is less, whereas in the Netherlands, they're putting gas into storage, so they get slightly higher summer prices. So that difference in price between summer and winter is less on the continent and greater in GB. And that has various impacts on different pieces of infrastructure, like gas storage facilities. They'll be more valuable in GB because you have that bigger seasonal spread. And then I've got a few cases here. I want to put in some things of where we have had weather, some examples of where weather has been seriously affecting the prices in GB and the Netherlands. So we mentioned that Hazel mentioned the beast from the east briefly, and that was quite a time in the gas market. I mean, this was before the Russia crisis, so at the time it was as bad as it had ever been seen. And it was a very cold, a long cold winter, where there was a cold patch in December that led to high prices and sort of emptied out storage considerably. And then there was this cold patch right at the end of the winter that's particularly impactful on gas markets, because you've used up your storage, thinking that it's going to be warm soon and we won't need it. And then if you have that really cold time, it's the 1st of March, that really, really high price day, storage is quite empty and you get a cold patch, then it has a much bigger effect on price. And then you've got the 21 winter. It was quite cold there in various places. That was when it was quite cold in the US, I think, and China. And so there was quite high gas demand. Now prices, that was still a very high price, really, actually, but it's just that the 2018 was so high, by comparison, it looks less. But you can see that generally the winter was not as cold. The 17-18 winter, I feel a bit nervous saying this in front of all these weather people who will know so much more about it. I've just got an average temperature. But so it wasn't anything like as cold overall in over 2021. But it was a long cold winter in the UK, which led to those very high prices. Also, over 21, you can see that the GB price was above the Netherlands price, and we were actually importing quite a lot of gas from the continent at that time, which helped keep the price down. But in the beast from the east, it was also extremely cold on the continent as well, so the gas wasn't available to import, which sort of pushed prices up a bit more. And I noticed something that Isla was explaining to me about the other presentation, about how predictable some of the forecasts were, that Russia was unpredictable, a little bit unpredictable. And in fact, the beast from the east, a lot of that came when demand is high in Russia, back when we had a lot of Russian gas on the market. When it was very cold in Russia, the gas doesn't always arrive in Europe because it was serving the huge Russian gas demand. So that used to be a very big factor, but now that Russian gas has come sort of like out of the picture, I think that's quite interesting, because perhaps how cold it is there will matter less. And that moves me on to Russia. So you will know that the Nord Stream pipelines are not operating anymore. They were actually, well, depending on how you see it, they're actually blown up. So there were 2 pipelines for each stream, and 3 of them are destroyed, but the other one isn't in use. So no gas is coming from Russia via that route. And no gas is coming via Poland. I'll put in the next picture here. So the Yamal, which is that bit of pale green, no gas is coming down there either since the invasion of Ukraine. Poland is not keen at all to have any Russian gas transiting there, and they're repurposing their part of the pipe. So very little Russian gas will be able to come via those routes. However, staggeringly, you'll see in this pale blue, this is the gas that comes, some of the gas that comes via Ukraine. In the much further back, a lot of gas transited Ukraine. But despite the war in Ukraine, still consistently since the invasion, there has been a lot of gas still transiting Ukraine. And some of these contracts which still exist for Russian gas have to come via Ukraine. So very recently, OMV, which is the Austrian gas company, the contract has been suspended from Gazprom. So that gas no longer needs to transit Ukraine, but despite that contract coming to an end because of a dispute between Gazprom and OMV, the volume of gas hasn't actually changed. So although it's not being sold via the contract, it's being sold on the spot market. So that's quite interesting. The same amount of gas is arriving, even though they've had an argument, but it did put prices up. They weren't happy about that. That worried people that this, although it's not huge compared to the amount of gas that used to come, it's still very important for that some of these states that are right in the centre of Europe and need that Russian gas. And then one of the outstanding things here, which is quite interesting, is that at the end of this year, at the beginning of 2025, the remaining transit contract for Gazprom across Ukraine actually ends. The Ukrainians have kept it going because they care about their European friends and they want to keep them supplied with gas, or these countries that have supported them. However, when it comes to an end, they may not wish to serve Gazprom anymore, and that's at the beginning of 25, at the end of this year. But there is still a contract that goes into Slovakia that's due to continue to 2027, and Slovakia is a very cold country, and it relies heavily on these imports and for heating. And although they can still get gas via other routes, it's not easy capacity-wise. There may be some restrictions. So there is some anxiety in the market about what will happen when that contract across Ukraine ends. This is all to give you some colour as to what's happening and why Europe might be more sensitive to whatever weather forecast you give us. These things matter because there's much more tension now without the Russian gas available. So I'm just ending on a quick history, a story of weather through the history of gas storage levels. So that was when it was very cold in Europe. It got very close to empty when the price went very high. That's the beast from the east. Then we have that cold beginning of 2021, where it's quite empty, but not as empty as it was at the beast from the east because there was that long prolonged cold winter. And then more recently, you'll see that gas storage has hardly been allowed to fall at all because the EU has put in some minimum fill requirements. So it just hasn't dropped below it. So that's a combination. It has been mild in both those winters. Equally, they've been really concentrating that if any gas is used in storage, they fill it back up as quick as they can. So that's the security of supply story. So I've gone through this quite quickly. It gives you an idea of what we think about when I'm thinking about gas markets and quite how simple we are compared to the meteorologists.
That was really interesting. So could I ask all of the speakers, please, to turn their cameras on and we'll go through the questions. I think first we just had a quick one for Lucy. So why is it more difficult to store gas in the UK?
Oh, it's not more difficult to store it. There's just less capacity. So we have about 7 fields, and they're mainly quite small. They're salt cavern storage where you leach out the salt and use it for gas, and then a couple of small old gas field and an old oil field, which means that they tend to turn around in a couple of weeks. So they can fill and empty anything from 2 weeks to a month. And we have one slow one, but it's not very big, we used to have a big offshore field, which gave you a whole winter. You could fill it up slowly in the summer and empty it slowly all winter, which would have been very useful. You know, I think it was nearly empty. Now you're testing on when it actually closed. But once it closed, it meant that we were more vulnerable to long, cold winters. So we were very lucky that it was after Russia cut off the gas, we were very lucky it was a mild winter, because we would have been short of, in a long, cold winter, we would have certainly been short of gas in the UK. The continent has got a lot more gas storage. Germany has got a lot of gas storage. About a quarter of all that's available across Europe is in Germany. But they had trouble, of course, filling it up when Russia cut off the gas. But we haven't got so much capacity. It's not hard. It's not harder to fill it up or empty it. It's just not very much of it.
Okay. Thank you, Lucy. So I think our next question, which Antje already touched upon, and I think Hazel also mentioned, was how much is this increased chance of mild winters due to a warming trend? And is there any way that we can sort of quantify this? Can we quantify sort of a thermodynamic component and then a dynamical component, or is that not possible? I guess we'll go to Hazel first and then maybe Antje.
Thank you, Ben. I saw that question, so I had a quick look back at the record. So I don't know if you remember, but I had a slide showing the last 10 winters and which category they fell into in terms of temperature. And it was something like 5 out of the 10 became a mild, which is, you would expect 2 out of 10 to be mild, but it was actually 5. So it's more than doubling of the risk. And the risk of a cold it was only one cold winter in 10. So the numbers point to the fact that we are getting warmer winters, but still, when we get the dynamics such that if we had a northerly flow or a strong easterly flow, you can definitely still get colder than average winters. So even though we're using a baseline from 1990 to 2020, and we always typically in meteorology use that 30-year period, it is more likely we're going to get that mild winter, but you still can get it if the dynamics is such that it gives you the northerly or the easterly flows.
And Antje, do you have anything to add on that, or has Hazel covered most of the points?
Yeah, perhaps just to say that, I mean, this is very much an attribution question, that in the seasonal community, perhaps we haven't paid as much attention as we can and should, but just haven't so far. So there's more to do to demonstrate or quantify that effect. Not that it helps us in the end, because in the global warming contributes to the forecast, is kind of included in the greenhouse gas or other radiative forcing components are included in our forecast. It's not that we don't account for it, but it would be good perhaps to see that quantified more. There are some studies, like scientific papers around, perhaps more for the summer season, because they're over Europe especially, see quite some impact. We should emphasize as well that there are regional differences in the imprint of the overall global warming. And as we heard from Lucy, especially if it comes to energy, we're not just looking locally in Europe, we're looking worldwide, and the impacts there might vary a bit.
Cool. Thanks. I think so the next question is again, I think for Hazel and Antje, thinking about the forecast outlooks for December versus the seasonal mean. So I think Alberta here is asking about when the NAO positive might enter the picture. So maybe this has to do with the sort of expected teleconnection with La Nina, but I don't know whether you could speak to that, Hazel, about the sort of precise timing and whether we can say anything about that.
Yes, so sorry, I've forgotten the name, but yes, the person asking the question was correct, that we're in with that. The model is basically going for a La Nina winter with a wet, windy, warmer winter in the latter half, so January, February, rather than in December. So as we said, in December, it's more of a high to the west of the UK, so actually a bit drier than normal. Still, mild, well, near normal temperatures, but drier and calmer, whereas the late winter is warm, wet and windy. So that's January, February.
And I guess I just had a quick follow-up question for Antje on this. So you mentioned I think it was the 2020-21 winter season, where it had the expected sort of teleconnections for La Nina, and that was forecast, but then that forecast bust in its sort of reverse sign. So what have you looked at that particular example, and what were the sort of interactions that caused that forecast to bust?
Yeah, it's an interesting question, and it's a difficult question. We looked a little bit, not super extensively, but other people in the community did. And it's not an easy one to answer, really. It isn't. In case people might remember, or the one event that perhaps stuck in your mind was the extreme cold spell in the US that reached sub-zero temperature in places like Texas, and where energy supply broke down for quite some time. So people speculated that stratospheric warming that happened at the beginning of January and that winter contributed to that extreme cold air outbreak, especially over the US. But I think modeling studies, people were very quick to speculate on that aspect, and it seems plausible, but modeling studies didn't confirm that. That wasn't with our model, it was an NCAR high resolution or specifically for stratospheric purposes model. They didn't find that link. So it's not as easy. I mean, there was also MGO activity in that winter. We didn't do an extensive case study on seeing what contributed to that. There's some, there's natural variability, there's unpredictability. We run 50 versions of our model in our ensemble system and try to compare that with the one realization that is observed that happens in the real world. So you do expect sometimes mismatches there, even though your model in a probabilistic sense gives you the right sense of it, say.
Yeah, I mean, Hazel, did you have anything to add on this?
Yes, Julia Lockwood did a study, because we typically do a study after every winter to look at how good our forecast has been. And Julia looked at this particular study with others here. And as Antje said, there was a stratospheric warming in early January, which then led to a cold January, February, amongst other things. And it was interesting, our forecast from the Met Office was for a warm, so similar to ECMWF, a warm, wet January, February, but actually from end of November. And I think but from mid-December, so 2 weeks ahead in the model, we started to get a signal for a stratospheric warming in early January. So 2 weeks ahead. So from mid-December, the forecast for January, February, March was for cold. So I think it just highlights the fact that currently the model wasn't capable of getting that stratospheric warming in January from the end of November. However, 2 weeks later it was. So I think it just highlights the point of having keeping abreast of the risk of a sudden stratospheric warming, and not just taking one seasonal forecast for the winter, but trying to keep up to date gives you the best information for if there is a change. And if we have got stratospheric warming, then often the forecast will change quite dramatically.
Yeah, definitely more.
And you still can get advance warning of it.
Yeah. Antje, do you have anything to add?
Yeah, just to add exactly on this point, as Hazel mentioned, the way the forecasts are run at the Met Office and at ECMWF is slightly different in terms of the start dates, but we will be introducing a new forecasting system next year called C6. And one of the changes from the previous system is that instead of initializing the forecast once a month, we will be in the new system do that twice a month, so at the beginning and in the middle. And the motivation was very much the one that Hazel mentioned, that we want to pick up some of the sub-seasonal variations in our initial conditions better, so that we can provide better prediction on these shorter timescales, basically.
Nice. Okay, so we'll just change focus here. So we'll go back to Isla and Lucy. So I guess maybe Lucy first and then Isla. So does the UK need to store more natural gas and electricity in the future? And if so, are there any plans to do this? And I guess Isla can talk more about how sort of weather and climate variability might be used to make decisions about this. But maybe
she might be able to talk a bit more about electricity storage as well than me. But as far as gas storage, that's a good question. There was a plan when Russia cut off the gas. The UK government became quite anxious about the fact we didn't have enough gas storage in this country, especially for that winter immediately afterwards. So there's this large offshore gas field, Rough, which I mentioned before, which was shut down because it had deteriorated. And the amount of money that needs to be invested in it to make it working again was so huge that price differential you saw that I showed at the beginning of my presentation wasn't going to be enough, to pay for it. especially with mild winters, because you don't really use it. It's there purely as a security, and it's a very expensive bit of security. So they've said they've reopened it, but I think what they're actually doing is there's a residual amount of gas in there, which they only take out in the winter. I'm not completely convinced they're actually able to inject much in the summer. So that is possible that they might try and enhance that and make that, give it more capacity and actually start injecting it and withdrawing a bit more. There's very little capacity available in that field at the moment. That could be beneficial. Shorter term storage, the one that empties and fills quicker, is useful to fill up the gaps with the wind you were talking about. So that's better when you're using gas to back up wind, then those shorter term facilities are good. So I don't think they're going to go out of fashion. I think we'll keep them. And also people talk about opening up hydrogen storage. There's a lot of talk about hydrogen replacing gas. So salt caverns, you can store hydrogen in salt caverns, but the problem with hydrogen, which I'll say, is that it's got about a third of the calorific value. So you get a third of the bang for your buck, in that you can store hydrogen in the salt caverns, but you have a third of much energy in them. So it's not quite as useful as a methane, as a storage. But here at AFRY, we do tons of stuff about batteries. And you do work with batteries with your...
Yeah, we do some. So I think somebody wrote an article just a few days ago actually about the low wind situation in Germany and like how much battery storage you'd need to cover it. And it's just like, so many times more than the battery storage we have at the moment. It's just inconceivable that you could cover periods like that. And I think it's an interesting question because as renewables have increased and as people think, power is easy to get, you look at things like AI, and we're guilty of it, I think, as meteorologists, and we don't really consider how much power we're using in order to do things that we don't necessarily need. And so I think, if you really want to go to net zero, then people might have to start thinking about their power usage a little bit more. In terms of batteries, then I think, batteries and hydrogen storage are going to be increasing. In terms of one way forward, if more people install solar panels in their houses and have localized batteries, like smaller scale batteries, to flatten out the curve, the demand curve, then that can make a big difference. But it's very much a behavioral shift that would be required.
Interesting stuff. I guess while we're with you both, I guess this is more a question for Isla, but how much is the wind speed forecast used by the energy sector? So both, I don't know, I guess short range and then sub-seasonal to seasonal range. Is it used at all? Is there enough confidence in the forecast, and how useful is it?
Yeah, so wind farms are dispatched, all the time. And they use the wind forecast. The ensemble approach is very useful. It's very clear. I mean, I think, the EC ensembles, but equally you could get ensembles from UK Met Office or GFS, but they have the EC hourly ones that are now accessible. The ensembles make it very easy to see when there's high confidence about different wind levels, and also when there's a little bit of mismatch in the different ensemble members about timing of low pressure systems coming through the UK and into the North Sea. I'd say the skill out to 5 days is pretty good usually. I mean, it obviously varies. If it's a stable weather pattern, you can get good skill even out to 10 days. You could get a low pressure system like Storm Bert coming through. In some areas, then it was maxing out, but in other areas, there was quite a lot of fluctuation about how strong it would be. So it does vary tremendously in terms of the skill horizon. But they're used, so day ahead, then you want to plan how you're going to ramp up your CCGTs. So you can't just flick a switch and turn gas turbines or coal turbines on. So you need a certain amount of time, when France brought the coal plant back on, having had it mothballed for a while, then you need a period of time, like days, in order to bring it back on. And so that's where the forecasts become really important. I think there's still we're not about to increase the skill horizon of wind forecasts out to 20 or 30 days anytime soon. But I think if we have an idea, like if the sub-seasonal forecasts start being able to flag up even if they can flag a regime shift, which makes it more likely to have more days with low wind, then it helps thermal plant to know when they can schedule maintenance or when they need to be available.
Right. I guess we're kind of getting towards time, but also I think we'll wrap up with a few more questions. So I guess just on that point, I guess for Hazel and Anja, how much skill is there in the wind speed forecast, and how does this translate into skill for wind power? So I guess how predictable is wind power in different regions over parts of Europe? I guess Hazel first, maybe.
Thank you. So again, Julia Lockwood did a paper looking at wind speed skill from the Met Office seasonal forecast system throughout the year, and the best skill was in December, January, February, over the winter period, and that is associated with our ability. So the UK sort of sits between those nodes of the North Atlantic Oscillation, and the winds are directly a function of that gradient. And so the fact that the Met Office system has got some skill in predicting that oscillation, and we do have reasonable skill in the wind speed over the UK. So we're talking a correlation, I think, of about 0.5, 0.6 Pearson correlation between the OBS and the forecasts, but that varies with season. So it drops down quite dramatically in summer, so we don't have skill. For most of the rest of the year, we don't have skill. So we do have skill in the East Atlantic pattern in the late autumn and early winter, which is important for our weather at that time of year. So there is a potential for improvement in skill in that season. I looked at temperature and rainfall, and we were able to predict temperature and rainfall in the UK with skill associated with that East Atlantic pattern. But I didn't actually look at wind power. But so best skill is in winter, when we have the best chance of getting the large scale drivers, and there's much lower skill the rest of the year.
I guess, would you agree, Anja? Is that typically the case for the European Centre forecasts as well? Do they produce any wind power forecasts?
We certainly don't produce wind power forecasts. That's not on our remit. We don't even have operational products for wind as a meteorological variable in the forecast. We just don't do that. You can get the data from our archive, and they're distributed. And I think the Copernicus Climate Change Service, they do have some forecasts for 10-meter wind, but I haven't seen the verification for those. However, knowing about the relationship of the dynamics and the wind, so say the pressure gradients and the pressure fields, you might remember the plot I showed from the skill of the sea level pressure forecast for winter that were noticeable for the gap of skill over the British Isles and sort of the eastern part of the North Atlantic. That's partly to do with the variation, the north-south variation of the strongest gradient of we can't locate, and where, if you have a strong gradient, where exactly this will be, which is important for the winds. So I can't say very much on that end there.
And maybe finish with one final question for Hazel. Can we say anything about maybe the number of extreme days that we might see in the winter from the seasonal mean, or are these two things unrelated?
Yes, so we've actually got Anna Maidens here at the Met Office doing some work looking at temperatures, but it's probably not too different to wind speed, where the seasonal mean in our neck of the woods is well correlated with the number of extremes. So specifically, she's looked at the risk of the coldest day temperature or the warmest day and how it relates to the seasonal mean, and there's a strong relationship between the two. So in our part of the world, that relationship is quite strong. In other parts of the world, it isn't, and it's sort of related to the large scale drivers. So yes, I think at the broad level, you can say that if we're having, for example, Julia did specifically look at this, the risk of if you have skill in the seasonal mean, you have some skill in the tails of the distribution, but it's not a one-to-one relationship. So you can always still have extreme periods that don't relate to the seasonal mean. But as a broad brush, you could use the seasonal mean as an indicator for your risk of extremes.
Perfect. Thank you, Hazel. And I think we're pretty much at time. So I don't know if we have any slides that we'd like to share on our end just to sort of finish off. I think that might be Abby. But otherwise, I'd like to thank all of our speakers for the great talks today and interesting questions. And I think we have some more information about keeping in touch with the Royal Met Soc. So I think some of this might be uploaded to YouTube, and you can also look at the event there. And like I said previously, if you have any questions, do contact us on that email there. So we've got 2 upcoming events, and we've got 2 upcoming events looking at the history of climate modelling and also weather and climate hazards for those in the insurance sector, looking at catastrophe models. And finally, I think we have Met Matters as well, which is sort of the newsletter for anybody interested in all things weather and climate. So I think that's it, and we're at time. And I'm going to be kicked out of my room. Thank you, everyone.
Thank you, Ben.
Thanks, Ben.
Bye-bye.
Bye-bye. Bye.
Thank you. Bye-bye.